Airplanes gain static electricity from friction with air, rain, and snow during high-speed flight. This energy builds up across the fuselage, concentrating primarily at the sharpest edges of the airframe.
As charges saturate, they ionize surrounding air molecules, leading to a phenomenon called corona discharge. These uncontrolled sparks create radio frequency noise, which can severely scramble essential navigation and communication signals.
To solve this, engineers install static wicks that allow electrical energy to bleed off continuously. These high-resistance devices prevent rapid sparks by dissipating the charge into the atmosphere at a controlled rate.
By keeping the voltage below the corona threshold, the wicks ensure clear, uninterrupted radio frequencies for pilots.
Lightning strikes often hit the nose, or wingtips, where the electric field is most concentrated during storms.
To protect the airframe, a conductive copper mesh is embedded within the composite skin of modern jets.
This creates a Faraday cage, forcing massive electrical currents to flow safely around the exterior fuselage skin.
Segmented diverter strips on the nose radome guide the strike away from sensitive radar equipment hidden inside.
The electrical energy eventually exits through the trailing edges, often utilizing the static wicks for a safe discharge.
Specialized surge protectors and heavy shielding prevent high-voltage spikes from damaging the aircraft's critical flight computers.
Icing occurs when supercooled water droplets freeze upon impact with the aircraft's leading edges during flight.
This accumulation disrupts airflow, reuses lift, and adds significant weight, creating a dangerous aerodynamic stall condition.
To combat this, jet engines divert hot bleed air through internal ducting to heat the wing surface.
This thermal anti-ice system prevents ice from ever forming by keeping the metal skin above freezing temperatures. On smaller turboprop planes, flexible pneumatic boots inflate and deflate to physically crack and shed ice layers. Electrothermal heaters are also used on windshields and pitot probes to maintain visibility and accurate flight data.
These sophisticated sensors and heating elements work in tandem to ensure safe operation through the harshest winter conditions.
Jet fuel is primarily stored inside the hollow wings, acting as a structural weight to balance aerodynamic lift.
Computer-controlled pumps manage the flow between tanks, maintaining the aircraft's center of gravity throughout the long flight.
In emergencies, high-volume jettison valves can rapidly dump fuel from the wingtips to reach a safe landing weight.
Fire detection loops monitor critical zones, using thermal sensors to alert the cockpit of any localized heat spikes. If a fire is detected, high-pressure halon bottles discharge a chemical cloud to instantly suffocate flames within the engine.
Nitrogen inerting systems replace oxygen in the fuel tanks with non-combustible gas to prevent any internal ignition.
These layers of containment and suppression ensure that fuel remains a safe energy source, even in extreme conditions.
Hydraulics act as the aircraft's muscles, using high-pressure fluid to move heavy flight control surfaces.
3 independent systems operate at 3,000 psi, ensuring full control even if one system fails. Fly-by-wire computers translate pilot inputs into precise digital commands for the hydraulic actuators.
Pistons made of high-strength titanium extend and retract to deploy the massive landing gear and flaps. Servo valves regulate the flow of fire-resistant hydraulic fluid with microscopic precision during every maneuver. If total power is lost, a ram air turbine deploys to provide emergency hydraulic and electrical energy. This robust network of pumps and pistons provides the immense force required to master the skies safely.
At high altitudes, the thin atmosphere requires the cabin to be artificially pressurized for passenger survival.
Hot air from the engine compressors is cooled and conditioned by air cycle machines, known as packs. The outflow valve acts as a precision vent, constantly regulating internal pressure by releasing excess air. If pressure is lost, emergency oxygen masks drop automatically, triggered by chemical generators or high-pressure cylinders. Integrated sensors maintain a precise balance of temperature and humidity to ensure comfort in the freezing stratosphere. Heavy structural seals and reinforced windows keep the internal atmosphere contained against the crushing external vacuum.
This life support network allows thousands of travelers to fly comfortably in the most hostile environments on Earth.
The landing gear must withstand massive impact forces while providing a stable platform for ground maneuvers.
Massive oleo struts use a combination of compressed nitrogen and hydraulic oil to absorb the energy of touchdown. High-torque electric or hydraulic motors drive the steering actuators, allowing the nose wheel to pivot with precision. Carbon ceramic brake discs utilize intense friction to convert the aircraft's kinetic energy into heat during high-speed landings.
Anti-skid systems monitor wheel rotation, automatically pulsing the brakes to prevent dangerous tire blowouts on wet runways.
Thermal fuse plugs are designed to melt and deflate tires safely if the brakes reach critical temperatures after stopping.
This robust mechanical assembly ensures a smooth transition from the high-speed sky to the safety of the Earth.